Hello. In this video, we are going to be looking back at sections 1.1, 1.2, and 1.3 and solving the problems involved there, the ones that have a context, our problem solving. So basically, word problems, okay? So we're going to be able to use linear equations. So we're going to use linear equations and a bunch of other methods to solve some real life problems. Okay, so our four-step approach. So we've got 4 steps in solving. First, understand the problem. Part of understanding the problem is asking, what are we trying to figure out? Okay, what are we figuring out? Meaning, what's our answer going to look like? What are we trying to figure out, and what is given to us? So what do we know? Those are the 2 most important questions there. What do we know, and what are we trying to figure out? Okay, once we have that narrowed down, we can start by making a plan. Okay, so making a plan might involve use one or more problem-solving strategies. And we'll go over the problem-solving strategies below. Okay, they're down here. Okay, so then we solve the problem. Okay, so actually carry out the plan. So carry out the plan. Checking your work as you go. Check it as you go. Okay, and the very last one, look back. Ask, does my answer, does it make sense? This to me is the number one thing to look at, is once you're done, does my answer make sense? Did what I get actually make sense in the context of this problem? For example, if what I'm trying to figure out up here, if in the problem I'm trying to figure out how many cats she has, and then down here my answer ends up being negative 457, my answer does not make sense with what we're trying to figure out. So you always want to basically connect our look back goes back to understanding that problem. Okay, so now let's look at some common problem-solving strategies. One is using a verbal model. What we mean by verbal model is AKA kind of write it out in words. Okay, use words and math symbols to kind of create an idea of what's going on. Another very popular one here is drawing a diagram. Sometimes you can go straight to writing an equation. This one is probably the least useful. Looking for a pattern. Okay, is there some pattern that you can go ahead and extend out to get to work out? Working backwards, starting at the end and working your way back to the beginning can be helpful. Guess, check, and revise. This tends to be the most popular for a lot of people. They just guess an answer, see if it works. Sketching a graph or a number line can be helpful. That's useful when you're talking about temperature or depth, as far as like going up and down on a number line. Making a table or a list, or break the problem into smaller parts and solve each of those themselves. Okay, so let's go ahead, and I think the best way is to just jump in and practice some. Okay, so here, a lot of times when solving problems, the very first step, understanding the problem, many times requires you to read the problem more than once. So in the 2012 Olympics, Usain Bolt won the 200-meter dash with a time of 19.32 seconds. Write and solve an equation to find his average speed to the nearest hundredth of a meter per second. Okay, so first understanding the problem. What are we figuring out? We're trying to figure out his average speed. So I'm going to go ahead and I'm going to write down here at the bottom his average speed was, and then I'm leaving a blank, was blank. And then it tells me here in this last, to the nearest hundredth of a meter per second. So I know my last needs to be meter per second. And I'm going to write it that way. Okay. Actually, I'm going to write it as a meter per second. Okay, so then I can tell here that just by writing my answer this way, we have meter over second, that to find this, I need to take my meters and divide it by my seconds. Okay, so does it give me my meters and seconds in this problem? Yes, it does. He won the 200 meter dash, so there's my meters, okay, in 19.32 seconds. So he went 200 meters per 19.32 seconds. Okay, and if I simplify that, that's going to give me my meters per second. So I'm going to go ahead and bring up a calculator. I need to take 200, let's get rid of those things, 200, and divide it by 19.32, and I get 10.35196, 10.35196, move that out of the way, okay, and that would be in meters per second. Okay, so now I think we kind of worked that one out. What are we figuring out? Did we figure out his average speed? It's 10.35196 meters per second. Let's read the problem one more time. In 2012 the Olympics, Usain Bolt won the 200-meter dash with a time of 19.32 seconds. Write and solve an equation to find his average speed. So here's our equation. His average speed is equal to 200 meters divided by 19.32 seconds. Okay, only thing we haven't addressed is this guy here, to the nearest hundredth of a meter. So now we need to round this guy to the nearest hundredth place. So here's tenths, here's hundredths. So we want to round to that place, so we look behind, it's a 1. So this would round to 10.35 tenths, hundredths of a second. Okay. All right. Next, example 4. On January 22nd, in 1943, the temperature in Spearfish, South Dakota fell from 54 degrees Fahrenheit at 9 a.m. to negative 4 degrees Fahrenheit at 9:27 a.m. How many degrees did the temperature fall? Okay, this is kind of a number line problem, so I think I'm going to sketch a graph or number line for this one. Okay, so I'm going to go ahead and I'm going to do a vertical number line just because talking about falling makes me want to go down. Okay, so the temperature in Spearfish fell from 54 degrees Fahrenheit. So we were at 54 degrees Fahrenheit. So I'm going to mark here we are at 54 degrees at 9 a.m. And it fell to negative 4 degrees at 9:27. So that tells me that it went down. Here we're going down to negative 4 degrees at 9:27 a.m. How many degrees did the temperature fall? Well, it had to go down from 54 to 0. So at some point here it reached 0. So it went down 54 degrees. So from here to here it went down 54 degrees. And then it went down another 4 degrees to get to negative 4. So it went down. So we would go down, would be negative 58. How many degrees did the temperature fall? It fell negative 58 degrees Fahrenheit. And we were able to do that using just a number line. So it fell negative 58 degrees. That's how far down. And we put the negative on it. This negative here is just giving us that direction and telling us the degree it went down, not up. Okay. All right, next. Here we're using the table. They give us a table. Use the table to find the number of miles x. So there's our variable. So I'm going to go ahead and highlight that. There's my variable x. You need to bike on Friday. So if you notice here, Friday's got the x in it in the table. So that the mean, okay, what the heck does mean mean? Number of miles biked per day is 5. So if we don't remember what mean is, then we would probably need to look that word up. Mean is another word for average. Okay. So how do we average a bunch of numbers? Okay. If we don't remember that, we'd have to look it up or ask a friend, how do you find the average? To find the average, you add all terms, then divide by the number of terms. So in this case, I have 1, 2, 3, 4, 5 numbers. So I would start by adding those up. So I would need to take 3.5, add 5.5, add 0, add 5, add x. And when I'm all done, I would divide that whole thing by the number of terms. We said there was 1, 2, 3, 4, 5 of them. So we divide by 5, and that should equal the mean. Okay, so this is actually what we have here is somewhat of a verbal model. Here we talked about using a verbal model. So here we have a mixture of symbols and words. Okay, so I would start here and I would add those up. So 3.5 plus 5.5, 5, 6, 7, 8, that'd be 9, plus 5 is 14. So we have 14 plus x divided by 5 is going to equal our mean. And if we go back and read in our problem, it says, so that the mean number of miles biked per day is 5. So we know we want the mean to be 5. So that equals 5. Okay, so there we have an equation. So now we can solve it. To get rid of this divide by 5, we would need to take both sides and multiply both sides by 5. So this 5 over 5 is going to give me 1. So I'm left with 14 plus x equals 25. And then now I would need to subtract 14 from both sides. 14, negative 14 is 0. X equals 25 minus 14 is 11. So we would need to bike 11. So I would write, you need to bike 11 miles on Friday. Okay. All right, last one. Oh no, never mind, I got 2 more. Okay. All right, so we have your school's drama club charges $4 per person for admission to a play. The club borrowed $400 to pay for costumes and props. After paying back the, typo, that should be loan, the club has a profit of $100. How many people attended the play? Okay. So again, your school's drama club charges $4 per person. So I'm going to kind of do a verbal. We get $4 per person. Okay. So I don't know how many people, but that's what I'm trying to find out. It says how many people attended the play. So I'm going to write here, blank people attended the play. So that's what we're trying to find out. So this right here is we're trying to figure out how many people. So let's use that for our variable. Let's let the number of people be x. So if I'm getting $4 per every person, I would take $4 times the number of people to be total money in. The total money we're making. So this is the total money we've got coming in. Okay. Okay, and then we borrowed $400 to pay for costumes. So this money coming in has to pay for our $400 for costumes, plus an additional $100 profit. So I can tell from that we actually made $500. So the total money that we had coming in, this total amount of money that we had coming in, has to be $500. The $400 for the costumes and props and the $100 profits. So I can now set up my equation. My 4x has to equal that 500. So now we solve that. Divide both sides by 4. X then equals 500 divided by 4 is 125. So 125 people attended the play. Does that answer make sense? Again, our last step of problem solving. Look back. Does it make sense? Would it make sense for 125 people to attend a play? It sure would. Okay. Now, last example. Okay, this one I think I'm going to draw a picture. Let's read and see what's going on. We have a boat, leaves New Orleans, and travels upstream on the Mississippi River for 4 hours. That 4 hours might be important, so I'm going to go ahead and highlight that 4 hours. The return trip takes only 2.5 hours because the boat travels 3 miles per hour faster downstream due to the current. How far does the boat travel upstream? So I'm going to kind of draw a picture. Here, let's make it blue for water. Okay, so we traveled upstream. So here, let's say this is New Orleans down here. We're traveling upstream for 4 hours. So on our way up, it's 4 hours. Okay. The return trip, so now we're going to turn around and we're going to go back down. That only takes 2.8 hours. Because the boat travels 3 miles per hour faster. So we're 3 miles per hour faster. Okay. How far does the boat travel upstream? So we're looking for how far does the boat travel upstream? We're looking for this distance. How far? So we're trying to find the distance is what? It's my D. Okay, so I'm going to write the distance upstream is blank, and my units are going to be here. Here it looks like we're in miles per hour, so we're probably going to deal in miles. Okay. So I was traveling some distance for some amount of time. Okay, so if you remember from science, we know distance equals our rate or speed times our time. So this distance upstream that we traveled is going to equal our rate, which we don't know. We have no idea how fast we were going, so we don't know our rate. Rate equals question mark. We don't know our rate, and we don't know our distance. But we know our time is 4 hours. And on the way back, our time here is 2.5 hours. Our distance is going to be the same. These two distances are going to be the same. So we're going to both use D. Okay. But my rate on the way back is going to be 3 miles per hour bigger than this rate over here. So whatever this rate is, R, the rate over here is going to be 3 faster. So rate plus 3. But their distances are going to be equal. Okay. So the distance on this side is going to equal, the distance on this side has to equal the distance on that side. Well, we know distance equals rate times time. So let's go blue upstream. Distance equals my rate, R, times time, 4. Okay. Well, now on the red, on the return back, distance equals rate, which is R plus 3, times time, which is 2.8. Okay. So there we've got our picture, and we labeled our picture with all of our information. And now we've got 2 equations going on. So how do we go about solving that? Well, distance equals rate times time. But these distances we said here are the same. Distance upstream is the same as the distance downstream. So this distance and this distance are the same. So that means this and this are equal. So I can put it together, and we'll have 4R. I just rewrote this guy here. R times 4 is 4R. I'm going to do the same on this side, 2.8 times R plus 3. So now distribute. Okay, so we'll have 4R, 2.8R, plus 2.8 times 3 is 8.4. I used a calculator on that, guys. So, okay, now I want to subtract the 2.8 from both sides. Minus 2.8R. Those add out. 4 minus 2.8 is 1.2. R equals 8.4. Divide both sides by 1.2. R equals 8.4 divided by 1.2, 7. But that's our R. So that is our miles per hour. So we have 7 miles per hour. So that was here, that is this rate over here. This blue rate is 7 miles per hour. But it wants to know distance, the distance upstream. Well, here we wrote distance equals rate times time. So distance equals my rate, we know now is 7, times time is 4, so we get 28. So the distance is 28 miles. Da, da, da. All right, so now your practice is going to be a worksheet. Please seek out help if you're stuck, because I will be looking at your work to see how you did it. And see me or